A dwarf planet 4 billion miles away is behaving in a way that doesn't fit any climate model scientists have ever built. And the more James Webb looks at it, the less it seems to follow the rules every other atmosphere in the solar system plays by. Researchers spent 8 years unable to even confirm this was happening, simply because no instrument was sensitive enough to see it clearly. Stick around, because I'm about to walk you through exactly what Webb found on Pluto, why it's raising more questions than it's answering, and what scientists still can't explain even after years of watching this tiny world closely. And hit subscribe now, because this channel breaks down real space science without the exaggeration. And Pluto still has more secrets worth digging into. Let's start with why Pluto needed a telescope like Webb in the first place. In July 2015, NASA's New Horizons spacecraft flew past Pluto after a 9.5-year journey, capturing humanity's first close-up look at this distant world. It had exactly one chance, a few minutes to gather as much data as possible before continuing on into the Kuiper Belt forever. What it found rewrote assumptions scientists had held for decades. A massive, pale, heart-shaped plain of nitrogen ice, mountains of water ice rising more than 10,000 feet into a hazy sky, layers of blue haze extending hundreds of miles above the surface. Pluto wasn't the dead, quiet world everyone expected. But New Horizons only got one look, then kept flying, leaving behind more questions than it could ever answer on its own. Before New Horizons, even the largest telescopes on Earth could only resolve Pluto as a tiny, blurry smudge of light. Astronomers could estimate its orbit fairly precisely, since that only required tracking its position over time, but its surface composition, and whether it even had a meaningful atmosphere at all, remained genuinely open questions for most of the 20th century. That's part of why the 2015 flyby felt so revelatory at the time, and also why it left researchers hungry for a way to keep studying this world after the spacecraft had already moved on for good. The flyby also revealed something that, in hindsight, should have been an earlier clue about just how active this small world really is. Pluto's surface showed remarkably few other moon or rocky body ever photographed up close. In planetary science, a heavily cratered surface generally indicates an old, geologically inactive world, since impact craters simply accumulate over billions of years, with nothing actively resurfacing them. Pluto's surface, by contrast, looked almost suspiciously smooth and young in places, particularly across that famous heart-shaped plain, now formally named Tombaugh Regio. Researchers eventually connected that smoothness to slow convection happening within the plane's nitrogen ice, essentially a very gradual churning process that keeps erasing old impact scars over time, another sign that Pluto was never the frozen, unchanging world it was originally assumed to be. If you're the kind of person who wants space science explained clearly instead of buried in jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. That's where Webb comes in, and here's the technical problem that made studying Pluto from Earth genuinely difficult for years. Pluto and its largest moon, Charon, sit so close, together in the sky from any telescope's point of view, that separating their individual heat signatures used to be practically impossible. Researchers working before Webb launched repeatedly tried to detect specific atmospheric signals, and repeatedly came up empty. Not because the signal didn't exist, but because their instruments simply couldn't tell how much heat was coming from Pluto, and how much was bleeding in from Charon sitting right next to it. Webb's much larger mirror and far more sensitive infrared instruments finally solved that problem, letting scientists isolate Pluto's own thermal signature cleanly for the first time. To put that technical challenge in perspective, Pluto and Charon are separated by only about 12,000 miles, a distance so small on an astronomical scale that from Earth, the T-O objects appear almost as a single blurred point of light through anything other than the most powerful instruments available. Charon itself is unusually large relative to Pluto, roughly half its diameter, making this pairing function almost like a double world rather than a typical planet and moon system. That closeness is part of why the two bodies are gravitationally locked together in such an unusual way, always showing the same face to each other as they orbit a shared point in space between them. For telescopes trying to isolate Pluto's faint heat signature specifically, that same closeness became a genuine obstacle, one that simply couldn't be overcome until an instrument as sensitive as Webb's mid-infrared camera became available. Starting in 2022, Webb turned its attention toward Pluto, and what came back wasn't just a prettier picture. It was a genuine puzzle. Back in 2017, planetary scientist Shi Zhang at UC Santa Cruz proposed something that sounded almost backwards. On Saturn's moon, Titan, atmospheric haze traps heat and warms the world below it. Zhang argued Pluto's haze might be doing the exact opposite, absorbing sunlight and radiating that energy straight back into space faster than Pluto's thin atmosphere could ever hold onto it. Not a blanket, but a radiator, actively bleeding heat away from a world that already had almost none to spare. If you found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. At the time, most of Jung's peers were skeptical, and there was no instrument sensitive enough to actually test the idea. That changed once Webb's mid-infrared instrument became capable of separating Pluto's faint signal from Charon's. A team led by astronomer Tanguy Bertrand at the Paris Observatory used that instrument to measure Pluto's atmosphere directly, and the results, published in Nature Astronomy in June 2025, confirmed almost exactly what Jung had predicted 8 years earlier. Pluto's upper atmosphere really is being actively cooled by the haze particles suspended within it, and it turned out to be roughly 30 degrees Fahrenheit, colder than earlier models had expected. Here's the question that finding raises, and it's a genuinely open one. If a hazy atmosphere this thin can actively refrigerate a world rather than warm it, what does that mean for every other hazy world scientists thought they understood? Researchers are now asking whether similar cooling effects might be quietly shaping the climate of Neptune's moon Triton, or even hinting at what Earth's own atmosphere looked like billions of years ago, long before oxygen ever built up in our skies. Confirming this mechanism on Pluto doesn't close the question. It opens up an entirely new one about how common this kind of atmospheric self-cooling might actually be across the solar system. This kind of finding also forces a broader reconsideration of how planetary scientists model atmospheres on any small, distant world with haze in its sky. Climate models, built around larger planets and moons closer to the Sun, generally assume haze behaves in a fairly predictable way, generally trapping heat, similarly to how greenhouse gases work here on Earth. Pluto's haze doing the opposite means researchers can no longer safely assume that assumption holds everywhere. Every hazy atmosphere discovered on a distant exoplanet from now on carries a genuine question mark attached to it, since scientists now know firsthand that haze can behave in ways that actively work against a planet's own heat retention rather than supporting it, an outcome nobody seriously considered as a realistic possibility before Pluto's own atmosphere forced the issue. To really understand how extreme Pluto's environment actually is, it helps to look at the raw numbers. Sunlight reaching Pluto is roughly 1,000 times fainter than sunlight reaching Earth, meaning even high noon there would look closer to a heavy twilight here. Surface temperatures generally sit somewhere between about -387 and -369 degrees Fahrenheit, more than 250 degrees colder than the coldest temperature ever recorded anywhere on Earth. At those kinds of temperatures, nitrogen, the same gas that makes up most of the air you're breathing right now, freezes completely solid. That's the environment Webb is trying to make sense of from 4 billion miles away, using nothing but the faint light this tiny world reflects back toward the Sun. There's a second mystery Webb helped deepen, rather than resolve. Even the extremely faint sunlight reaching Pluto is enough to break apart methane molecules high in its atmosphere. Those fragments recombine into heavier compounds called tholins, reddish-brown particles that drift down and settle onto the surface. This process has apparently been running for roughly 4 billion years, a slow, continuous snowfall of organic building blocks landing on a surface too frozen for any of it to ever spark into something alive. Tholins belong to the same broad family of molecules some scientists believe may have once rained down onto early Earth, potentially contributing raw material for the chemistry that eventually led to life here. Pluto, in that sense, may be one of the closest things researchers have to a working laboratory for conditions that existed before life ever began anywhere, and scientists are still working out exactly how far that comparison can be pushed. Studying tholins directly is extraordinarily difficult under laboratory conditions on Earth, since replicating billions of years of continuous, extremely low-intensity chemical processing simply isn't something researchers can compress into a reasonable experiment timeline. Some laboratories have attempted to create tholin-like compounds by exposing methane and nitrogen mixtures to ultraviolet light or electrical discharges, producing reddish-brown residues that share some chemical similarities with what's observed on Pluto and other outer solar system bodies. But these lab-created analogs remain imperfect substitutes for the real thing, formed under conditions that can only approximate rather than truly replicate our billion years of accumulated chemistry happening in genuine deep space, vacuum, and cold. That gap between laboratory simulation and the real environment on Pluto is exactly why direct observations from instruments like Webb remain so valuable, offering a genuine window into chemistry that simply cannot be fully recreated anywhere on Earth. Then there's Charon, and the questions only multiply from there. Pluto has been slowly leaking methane into space for billions of years, and for a long time, nobody knew exactly where all of that escaping material was going. It turns out Charon's poles, stained a deep reddish-brown unlike anything else on the moon, are acting as a cold trap. Because of how Charon is tilted, its northern pole spends multiple decades in complete darkness. freezing incoming methane solid until sunlight finally returns, and cosmic radiation locks it into the same kind of heavy, reddish compounds found on Pluto itself. This entire mechanism represents a genuinely unusual kind of relationship between two orbiting bodies, one that researchers have taken to describing almost like a slow, one-directional atmospheric exchange between Pluto and its largest moon. Material, genuinely, leaves one world and ends up permanently altering the surface chemistry of another, a process that plays out over such an enormous timescale that no single human observation could ever capture it happening in real time. Instead, scientists have had to reconstruct the entire process indirectly, piecing together clues from surface coloration, seasonal modeling of Charon's decades-long polar darkness, and laboratory experiments simulating how methane ice behaves when exposed to cosmic radiation over extended periods. That reconstruction fits the observed evidence remarkably well, but it remains fundamentally an inference built from indirect clues rather than something anyone has watched happen directly from start to finish. In October 2024, a team led by researcher Sylvia Protopapa at the Southwest Research Institute used Webb data to confirm something new sitting on Charon's surface, both carbon dioxide and hydrogen peroxide, frozen directly onto the moon. The carbon dioxide most likely came from underground material exposed by impact craters. The hydrogen peroxide appears to have formed through years of radiation striking Charon's water ice. Researchers noted this specific chemical combination had never been confirmed on Charon before, and it remains an open question exactly how much more chemical complexity is still hiding on a moon most people assumed was just plain, unremarkable water ice. That discovery matters beyond simply adding two more chemical compounds to Charon's known inventory. Hydrogen peroxide, in particular, is a genuinely reactive molecule, one that doesn't tend to persist for long periods without either breaking down or reacting with something else nearby, which raises its own question about exactly how much of it remains frozen on Charon's surface at any given time, and how quickly that inventory gets replenished by ongoing radiation exposure. Researchers studying icy moons elsewhere in the solar system have flagged similar reactive compounds as potentially significant for understanding surface chemistry more broadly, since molecules like this can sometimes serve as an energy source for chemical reactions that wouldn't otherwise occur in such a cold, low-energy environment. Whether that has any broader significance for Charon specifically remains, like so much else about this system, a genuinely open question researchers are still working through. The biggest open question of all sites beneath the surface entirely. South of Pluto's famous heart-shaped plain, two enormous isolated peaks rise from the landscape, one roughly 13,000 feet tall, the other close to 20,000 feet. Both have deep depressions at their summits, ringed by fractures with lumpy flanks resembling cooled lava flows, except there's no molten rock on Pluto. If these are what they appear to be, they're cryovolcanoes, structures that once erupted with a slurry of water, ammonia, and methane forced up from deep beneath the icy crust. Researchers remain genuinely divided on exactly how these particular formations came to exist, whether from a handful of massive eruptions concentrated in a relatively short window of geological time, or from many smaller events spread across a much longer stretch. Either interpretation points toward the same underlying conclusion, that something beneath Pluto's frozen shell was, at some point in its relatively recent geological history, warm enough to force liquid material all the way up to the surface. Mapping the exact boundaries and internal structure of these features remains difficult using existing data, since New Horizons only managed to photograph this specific region from a single flyby angle, leaving researchers without the kind of multiple perspective imaging that would normally help clarify a formation this ambiguous. That internal warmth points toward one of the most debated ideas surrounding Pluto today, a hidden ocean buried roughly 100 miles beneath the surface, kept liquid by the slow radioactive decay of elements in Pluto's rocky core. The evidence is a pattern, not a photograph. Cracks and ridges line up in a WA, eyes that fit a subsurface layer of liquid water shifting beneath the crust, and that heart-shaped plain sits directly above a positive gravity anomaly, a spot where something denser than the surrounding ice may be concentrated. Similar hidden oceans are already strongly suspected beneath Europas and Enceladus. If a body as small and cold as Pluto is hiding something similar, buried oceans might be a far more common feature of icy worlds throughout the outer solar system than anyone assumed. It's worth explaining why scientists find this buried ocean scenario so genuinely compelling, even without any direct proof. Both Europa and Enceladus show far more obvious surface evidence supporting their own suspected oceans, including active geysers of water vapor erupting directly into space in Enceladus's case, something no spacecraft has ever confirmed happening on Pluto. That means Pluto's case for a hidden ocean rests on comparatively indirect evidence, gravity measurements, and surface cracking patterns, rather than any observed eruption of water vapor into space. If confirmed, It would suggest liquid water can persist far longer and far further from the Sun than most planetary scientists previously assumed possible, fundamentally expanding where in the solar system researchers might realistically look for environments capable of supporting the basic chemistry associated with life. Right now, there's no way to confirm any of this directly, and no funded mission planning to send a probe back to find out. The journey alone would take the better part of a decade, and outer solar system exploration has rarely been treated as a funding priority. Missions to this part of the solar system are extraordinarily expensive and extraordinarily slow, often requiring a full decade or more of travel time before a spacecraft even reaches its target, followed by a single brief window to gather data, much like New Horizons experienced back in 2015. Space agencies generally have to weigh a mission like that against many other competing priorities, including missions closer to home capable of returning results within just a few years instead of a few decades. That trade-off means distant, icy worlds like Pluto often lose out in funding decisions, not because scientists have stopped finding them interesting, but simply because the practical cost and timeline involved make them a much harder sell compared to closer, faster missions. For the time being, Webb remains the only working tool, quietly checking back in every few months whenever Pluto swings into its field of view, adding another data point each, time and almost always making the overall picture stranger rather than simpler. It's Wart H, remembering that Pluto is not unique simply because of its location. It sits inside the Kuiper Belt, a vast ring of icy debris beyond the orbit of Neptune, home to hundreds of thousands of objects wider than 60 miles, along with an estimated trillion or more comets. A handful of other bodies out there, including Eris and Makemake, come reasonably close to Pluto's size. Only one, the spacecraft, New Horizons, has ever ventured deep enough into that region to closely photograph any of its larger residents. And even that mission only managed close flybys of two objects, Pluto and a much smaller, more distant body nicknamed Arrokoth. If Pluto is genuinely cooling its own sky, slowly bleeding its atmosphere onto a companion moon, and possibly hiding a liquid ocean beneath a shell of solid ice, there's no obvious reason to assume it's the only object out there doing anything like this. It's simply the one close enough and bright enough for our current instruments to study in real detail. Nearly everything else scattered across that same enormous region of space remains almost entirely unobserved, meaning every open question Webb has raised about Pluto specifically might also apply in some form to hundreds of thousands of similar icy worlds that nobody has ever had the chance to study closely at all. So what does all of this actually add up to? Every answer Webb has provided about Pluto has come attached to a new question researchers didn't have before. A haze that cools instead of warms. An organic snowfall that's been falling for billions of years with nowhere to go. A moon quietly collecting. Chemistry nobody expected to find there. And two mountains that might be pointing toward an ocean nobody can currently prove exists. That's really what makes Pluto worth continuing to watch. Not that scientists have it figured out, but that every new observation seems to widen the gap between what they expected and what's actually there. It's also worth remembering just how young this specific chapter of Pluto research really is. Webb has only been observing this world since 2022, meaning essentially everything discussed here emerged within the last few years of a mission that could easily continue producing new Pluto data for another decade or more. Compare that to how long Earth-based telescopes struggled to learn almost anything definitive about Pluto throughout the entire 20th century, and the pace of discovery since Webb came online looks genuinely remarkable, even with so many of the resulting questions still sitting unanswered. If space stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because Webb is still pointing back at Pluto every few months, and there's a real chance the next round of data raises even bigger questions than this one did. Thanks for watching, and I'll see you in the next one.